So today we'll be doing 2023 May paper 2, Timezone 1. This is again a calculator paper, so have your TI calculator ready as well as your formula booklet, and we'll be going over this 90-minute paper, which is worth 80 marks. So let's start from section A. So number 1, we have 3 cities, L, J, and D, and they're represented on the diagram here, and we have some bearing notation. So the bearing of D from J is 34 degrees. So from J indicates that this is our reference point. So north from J is going to be 0 degrees. And the bearing from D from J, so this angle is going to be 34 degrees. And we look for other hints given in the problem. The city Lucknow, L, lies directly east of Jaipur, J. So you know that this is going to be 90 degrees because east, the bearing of east from north is 90. So we know that this is going to be 56 degrees, and let's look out for what else the question wants, right? So first, you have to find what JDL is. So we want to look for this angle. So I would first start by saying angle DJL is going to be 90 degrees minus 34 degrees, which is 56 degrees. Then, using the fact that the 3 triangles, the 3 angles should add up to 180, I would go with angle JDL is 180 degrees minus DJL, which is 56 degrees, minus DLJ, 25 degrees. That will give us 180 minus 81, or 99 degrees. So we're done with part A. Part B. We need to find the distance between L and D. So we want to find this length right here. So I would try to set up a sine rule relationship because first we have 2 pairs of a side and an angle. So the first pair is going to be 500 kilometers over sine 99 degrees. That is going to equal the length of LD over sine DJL, which is 56 degrees. So if you isolate the length of LD, that's going to be 500 times sine 56 degrees over sine 99 degrees. And the units you should keep as kilometers. So if you put that in your TI calculator, we should get something along the lines of 419.685, which rounds to 3 sig figs, that's 420 kilometers. So cautionary note must be you have to use degrees, not radians, in your calculator. So always check if your settings are in the appropriate manner. Right? So you have to do it in degrees, not radians. So a lot of the time students ask, like, when do we use degrees, when do you use radians? So when the question explicitly states quantities that are in degrees, we use degrees. Everything else we use radians. Okay, so we'll look at that again later, but for this case it's definitely a degree problem. So A, JDL is 99 degrees, B, the length is 420 kilometers. Okay, so that's number 1. Let's move on to number 2. Number 2, we have a sequences and series problem slash interest problem. So let's look at what we're given here. We have a car whose value is going to decrease because we know that we're multiplying a 0.91 each time. So cars are a depreciating asset because the first year you buy it, it's all shiny and new, but as time goes on, there's going to be wear and tear. You're going to need to take it to the mechanic, and it's not worth as much as time goes on, right? So we can kind of get that hint from this expression. So first it says, what's the annual depreciation rate of the car? What I would set up is I would go with the T and the costs. Right? So at time 0, we might start off with $40,000. So the car is worth $40,000, but 1 year later, what we're doing is we're multiplying a 0.91 once. So we get 40,000 times 0.91. The next year, we're going to be multiplying a 0.91 squared to 40,000. So that's 40,000 times 0.91 squared and so forth. So we know that from each period to the next, we're basically getting 91% of what it was worth before. That means it's losing 9% of its value from the previous year. So the rate of depreciation is going to be 9%. Next, if you were to find the value of the car on January 1st, 2028, and the starting year is 23. So 2023 is here, 2024, 2025, and if you want to go all the way to 2028, we know that t has to be 5. So we basically have our function for cost, right? Cost as a function of time, and we substitute in t equals 5 there. So that should give us somewhere around 24,961.28 Canadian dollars, CAD, or no, USD, US dollars. So if you round this to 3 sig figs, we would write this as $25,000. Okay, so that's what the car is going to be worth 5 years later in the year 2028. Okay. Next, we have Alvi who wants to start investing so that he can buy a car. So his investment is appreciating at 3% interest. So if you start off with $100, the next year it's going to be 103. The next year it's going to be 103 times 1.03. So we're going to keep compounding 3% from the previous year. So we need to talk about like what this money will be worth in 5 years' time. Okay. And then we need to subtract the value of the car back then. So basically we need to find out how much extra money he would need. So let's first talk about how much Alvi's money is going to grow as, right? So this is going to be 15,000. And for each year, we're going to multiply this by 1.03. So when t equals 5, right, at the year 2028, his money will grow to somewhere around 15,000 times 1.03 to the power of 5, which is going to be 17,000. So if you do that, that's going to be worth around 17,389.11 US dollars. And we found out earlier that the car will be worth around $24,961.28. So since his money has grown from 15,000 to 17,000, that's impressive, but not enough yet. So what we got to do is we got to subtract. So if you subtract this, we should get 7572.17. Rounding this should give us $7,570. So this is M. This is the money that Alvi needs to supplement in order to buy the car. So with these types of problems, the calculations are pretty simple. We do see a geometric sequence, but that was about it. We didn't need to add any terms. There was no like series formulas involved. But one thing I want to emphasize is always try to store values as precisely as possible. So I know that when you're writing out answers like mid-stage, we might want to round to 3 sig figs. But the thing is, if we're using this value later on in the problem, we don't want to substitute in this rounded value here. We want to substitute in the original values that are stored in your calculators, right? And we try to round at the very end, because if you round midway, we will lose some detail, and in some problems that might lead to some problems. Okay, so always try to store precise values on your calculator, and always reserve rounding to the appropriate sig figs to the very end if possible. Okay, so that's like the main takeaway from this problem. Okay, so there's part A, B, and C. The car depreciates at 9%. 5 years later, the car is going to go from $40,000 to roughly $25,000. Someone who's investing like $15,000, he's going to get $17,000, but that's not enough. So we need 7,500 more US dollars in order to buy that car. Okay, so that was question number 2. Okay, next, let's move on to number 3. We have two functions, f and g. First one is just asking us to find the expression for this composite function. And then we want to graph this. Okay, so let's first find what a is going to turn out to be. So if you have f is a function that takes in a x and it outputs a 2x minus x cubed. So anything that goes inside this mysterious function box of x is going to come out with 2 times x minus x to the power of 3. Now, if we have f of g of x, we can write this as a function within a function. So instead of putting a ordinary x here, we're instead putting a g of x here. G of x, which we agreed upon was tangent x. Right? So instead of x, we're putting in a tangent x. So the same thing happens. Instead of 2 times x, we get 2 times tangent x. Instead of the cube of the original value, we're going to get tangent cube x. So the expression we're looking for is basically going to be 2 tangent x minus tangent cube x. So that's part A. Next, we have part B. We want to sketch the graph y equals f of g of x for this domain. And we want to label the coordinates of any max or min points. Okay, so there's no way that we're going to be able to sketch this by hand or try to get a rough detail in our heads. So I suggest just going straight over to the calculator. And note that we don't need to sketch the whole graph. You just need to show it for this axis. So it's convenient because the question tells us we need to set our windows to -1 to 1, and y goes from -2 to 2. Okay, so let's move on to the calculator to see what we get. So if you go to your graph, we input our equation of 2 times tangent x, and then we do minus tangent x, and we cube that. Okay. So this is the graph we get. It seems pretty hectic, but that's because we are too zoomed out. So we want to go to Windows. We want to zoom to what the question wanted, right? So the question wanted x to go from -2 to 2, and it wanted to have y going from, actually x was from -1 to 1, and y was from -2 to 2. So let's make those changes. And we'll see a more focused, zoomed in, easier to see graph. Okay, so this is what you get. We always want to label any x and y intercepts as well as local max and min points. I think this question just wanted to look at the local min and local max, right? So what we do is we go to Analyze Graph, we look for the local min. So I want to find my minimum that's between these 2 points. So the lower bound is somewhere here. Upper bound is somewhere here. Right, so the calculator returns us the local max, local min value that's between 2 boundaries. I do local max again. So find me the local max that's greater than, say, 0.4, and that's less than somewhere around 1.2, right? So our local max is clearly between there. So we found these 2 points, 0.685, 1.09. Right? We could find that this is the 0 intercept. So even though it looks like it's passing through the origin, never assume that. We always want to confirm that, right? So we might want to say, what's the 0 between these 2 points? Okay, so we know it passes through 0, 0, so we can include that detail. Right? So when it comes to sketching this graph, what we got to do is we want to make sure that when we're sketching this graph, we want to make sure to include any and all details, right? So we figured that it passes through 0.685, 1.09. So that's somewhere around here and somewhere around here, right? So this is 0.6, 0.7, so 0.685 is going to be somewhere around here. The y point is going to be slightly above the 1, right? And then we have negative 0.685 and negative 1.09, so it's slightly below the -1 mark, somewhere around here. And then we can trace our curve as going somewhere like that. And that right here. don't want it to be too straight. We want to do it like that. Okay, and the x-intercepts were clearly less than 1 and greater than -1. And we want to label the coordinates of any local max and mins. So we just want to label these 2 points right here. That's the first one. Second one is 0.685, 1.09. I think labeling the origin is optional, but since this problem didn't request that, you're not going to get any extra points for that. Okay, so that's number 3. All right, let's now move on to number 4. It seems like we have a typical regression problem, but you'll realize that there's 2 things going on. First, we're taking temperature, the highest temperature of the day, T. That's going to be our input. That results in the number of children visiting the park, right? So we know that these two might be related. If it's too warm, the children might stay in. If it's too cold, the students or children might not come out, right? So I guess temperature kind of affects how many children come out to play on the park. And in the second part, the number of children determines how much ice cream is going to be sold. So we have a model that takes the temperature of the day that outputs the number of children, right? So depending on the temperature, the number of people like turning out to the park is going to change. And the number of people who are potential customers of ice cream, that's going to determine like how much ice cream is going to be sold. So temperature affects how many children come out, and how many children are playing affects how much ice cream is being sold, right? So usually we kind of have x as the independent variable and y as the dependent variable, but this case it's switched. It's the y that affects x. So don't get confused. I think that's like the point of this problem. Like we're so used to using y as a function of x, but in other problems you might see these variable names and symbols switched around, but focus on like what's affecting what, right? What is the independent variable and what is the dependent variable, right? So as long as you have that clear image of what variables are influencing the other ones, that shouldn't be too confusing. So let's first look at A. Use this model to find the estimated number of children in the park when t is 25. Okay, so first part, you just substitute in t equals 25. So 0.6 times 25 squared plus 23 times 25 plus 110. That's going to give the number of children we have. So you just put that on your calculator. We should get roughly 310 children. Okay, so we might have an added value of 310. So based on these data points, we know that we're going to get somewhere between 23 and 35 ice cream sold, because 310 children is going to be here. We want to find out what that is, right? So in order to do that, we got to have a regression equation that predicts the number of ice cream sold when there are y children in the park. Okay, so the equation we're looking for is if we have our L1 as y, the number of children, and our L2 as x, the ice cream sold, we want to basically find x equals m times y plus b. Right, so using our calculator for linear regression, that's going to give us m and b. And for any input value of y, we're going to get x. So you got to write down your function or your list of all the children and the matching ice creams sold. And putting this in your calculator should output a certain function. Okay, so let's do that right now. So what you want to do on your calculators is you want to go to lists and spreadsheets. You want to put in your data. So you have your number of children, which is going to be 81 children first. So we have 81 children on the first case, 175, 202, 346, 360. And then the number of ice cream sold on each day is 15, 27, 23, 35, 46. Now, note that even though we had an additional number, like 25 degrees, so when it's like 25 degrees, we get 310 children, we don't put 310 on here because that's not a data point here. That's what we're trying to predict. So we're trying to predict the sixth data point for when there is 310 children. What's the number of ice creams sold? Like, we're not using that to build our model. When we're building our model, like when we're building our linear regression model, we're only using these 5 data points to find this mx plus b equation. And then we're adding the sixth data point there. We're adding, like, for this new set of y value, which was 310, what's going to be the x value of ice cream sold. Okay, so for now, we're only going to save these 2 lists. Let's call this one list A. Whoops. Nope. Okay, so this is list A and this is list B. So let's try to do actions. So let's try to do a stat calculations for linear regression. So we can set up a linear regression here. The X list is going to be A, which is our Y, the children. So we have A. Okay. And then we get B, right? So our X list is going to be the number of children. Our B list, our Y list is going to be the ice cream sold. And I just want to add the symbols for brackets here. So let's just make sure to add the bracket signs here. And the calculator should do the rest for you. We should find our equation of 0.0935x plus 7.43. Okay. So our regression model looks like x equals 0.0935y plus 7.43. So if there's y children coming in to the park, then the ice cream sold is going to be 0.0935 times the number of children, and then we add a 7.43. Okay, so the appropriate regression equation will be this right here. So the 3 points are based on how well you use your calculator. If you switch the x and y, you're going to have a bad time, right? Don't just think x is always the independent. Always remember, like, what the question is suggesting in this scenario, right? So that's part B. Next, part C involves using this equation to precisely find out what's the number of ice creams sold. So when T is 25 degrees Celsius, the number of children was 310. So x is going to be 0.0935 times 310 plus 7.43. So if you use that equation, we're going to get somewhere around 36.4. So we're going to get 36.4, or we're going to get 36 ice creams sold. Right, so once you found your regression equation in part B, the rest is a piece of cake. We just got to substitute in our target value. Right? And then that says we're going to sell 36 ice creams. Let's now move on to number 5. We have a statistics problem. So D is normally distributed. So this company is going to manufacture a bunch of bicycle frames. So it's going to make 1, it's going to make 2, it's going to make 3, and it's going to make actually hundreds and thousands, right? I mean, it's a factory. They're going to make a ton of these bicycle frames. And I guess if you measure each and every one of these, it's going to be D, right? So let's say that the measurements is going to be in D millimeters, diameters of this tube here. So we're going to sample a very large number of these tube diameters, right? And it says D is normally distributed as a with a mean of 32 and unknown standard deviation sigma, right? So we have our variance being sigma squared, which is unknown. Okay, so what this is saying is that sometimes the bicycle frame might have a diameter of 32 millimeters. Other times it might have 33 millimeters. Other times it might have 31.9 millimeters. Other times it might have 33 millimeter, 33.1 millimeters. It might have like 32.4 millimeters. It's going to be all over the place. But if you keep on repeating these measurements, we're going to see that its mean, its average is centered around 32 millimeters. Right? And most of the bicycle frame diameters will be around that much, with some higher, some lower than that, but it's going to look like a normal distribution. Right? So what we mean by this d variable being normally distributed is that we're going to repeat our observations. We're going to repeat our calculations, measurements, observations of very numerous trials of these bicycle frame tube measurements. We're going to see values that are going to fall under this frequency, right? So most will be centered around 32. Some will be greater, some will be smaller, but we'll see like lower frequencies of extremely high or extremely low measurements. Then it says the interquartile range is 0.28. So IQR, which is a third quartile, the top 25%, minus the first quartile, the bottom 25%, is going to be 0.28 millimeters. So if we have Q1 here and Q3 here, what that means is 25% of bicycles will be shorter than Q1. 25% of all these tubes will be greater than Q3. But the difference between this is going to be 0.28 millimeters. Right? And note that this is a symmetric distribution. So the mean is perfectly at the center. Q1 and Q3 are equal distances from that. Right? So this is going to be 0.14. This is going to be 0.14. Right? So the quartiles are going to be 0.14 millimeters away from 32. So let's update that. Q3 is going to be 32.14. Q1 is going to be 31.86. Okay? And we need to find what sigma is. Okay? So whenever we don't know mu or sigma, so I would like to emphasize that when full info of a normal distribution is not known. Right? So in order to fully describe our normal distribution here, we want to know both the mean and the sigma. But when one or both of them are not known, we always resort to our standard normal distribution. So our standard normal distribution is associated with the letter z. Right? So z is basically a normal distribution with mean 0 and sigma or variance 1. So what we can do is we're going to assume that if we have a normal distribution with mean 0 and sigma 1, what's the value here? Right? What's the value here that's going to contain the lowest 25%? Right? Or what's the value here that's going to have the higher 25%? Right? So this is going to be known as a z-score, which can be converted by x minus mu over sigma. So for some variable x, right? So if you have our 31.86, we can subtract that from the normal, right? And dividing that by sigma shows how many standard deviations are we above or below the mean. That's going to be our z-score, which is this right here. Okay, so we're going to go to our calculators. We're going to find the z-score for the bottom 25%. And we're going to say that 31.86 has that z-score. What's the sigma? Okay, so let's move on to the normal inverse case. So inverse normal to find this. Okay. So in our calculators, what we're going to do is we're going to say we're going to have a normal distribution where the mean is 0, sigma is 1. And I want you to find the z-score, or I want you to find the value that's going to contain the lowest 25%. Then the calculator will give us this z value. And this is the z value associated with Q1, for which we know is 31.86. Okay, so then we're going to work out what sigma is. We're going to use stats. So we'll go to stats, distributions, and we do inverse normal. So when we know what mu and sigma are, we would use normal CDF. But since this is not such a case, we're going to do inverse norm. So as I've said earlier, we're going to look at the bottom tail, the bottom 0.25 of our normal distribution with mean 0, sigma 1. That's going to be negative 0.674. Okay? We're going to say that this is negative 0.674. So we have two normal distributions, right? So if this is 0 and if sigma is 1, then the bottom 25% is going to be a z-score of negative 0.674. Right? In parallel, we have our original distribution. Same normal distribution, same shape, same everything. It's just that the scales are slightly different. Right? We have mean as 32, so the center has slightly shifted. And then we're going to have the same, like bottom 25%, 0.25, 0.25. But this time, this is known to be 31.86. We could use the other case. So if you put an inverse norm 0.75, we know that we're going to look at the top 75%. So the right tail has an area of 0.25. So that's going to have a z-score of 0.674, or in our original case, it's going to be 32.14. Right? So either way, we're going to set up an equation where negative 0.674 is 31.86 minus 32 over sigma. Or if you went with the positive end, 0.674 is 32.14 minus 32 over sigma. Either way, sigma is going to be 0.14 over 0.674, which is roughly 0.208 millimeters. Right, so what this says is, if we have a normal distribution whose mean is 32, right, and if you want to say that 31.86 or 32.14, if you want those measurements to contain like 25% of the whole population under them, right, on either side, then the standard deviation must be pretty small, right? So it's pretty interesting because 0.14 millimeter is not that much, right? So we just move slightly to the left of the mean, and that's already 25% of the entire distribution. So we know we have a pretty centered distribution, right? So the main takeaway for these types of problems, just know this formula. Z is x minus mu over sigma. Z basically looks at the normal distribution where mean is 0, standard deviation is 1. Okay? So this is a diagram you want to focus on. The main tool we used in our TI calculator was inverse norm. Okay? So our sigma, our standard deviation, turns out to be 0.208 millimeters. Next, we have a binomial expansion problem, right? So we have ax cubed plus b to the power of 8. That's going to have a 448 x cubed term. And ax cubed plus b to the power of 10, that's going to have a 2880 term. Okay. So let's just quickly recap what this binomial expansion is, right? So if you have a plus b, that's just a plus b. If you have a plus b squared, that's a binomial term, a plus b, that's expanded, right? So we would have a plus b times a plus b. So how do we expand this? Well, we got to map out each and every term, right? So we take this term, this term, this term, and this term. So we get a squared plus ab plus ba plus b squared, which turns out to be a squared plus 2ab plus b squared. If we do it 3 times, right, we have 3 multiples of a plus b. It's going to get a bit tricky, but the idea is the same. We try to find one term from each binomial. So for instance, the first term might involve taking the first terms, right? A times a times a. Then we got to add the other cases. Like, what if we choose 2 a's and 1 b? So we might do like a, then b, right? So we would have a squared b. But there's not just one way to do it, there's 3 ways to do it, right? Like we could do a, b. So the b would be on the third term. We could also do like b, a, where the b is taken from the first term. Or we could do b, a, right? So there's actually 3 instances where a squared b is possible. Similarly, we could do ab squared, right? So how many ways can we take 2 b's and 1 a? We could do abb, BAB, or BBA, right? So there's 3 ways to do that. Then there's only one way to take b times b times b. So we would do b cubed, right? So there's a pattern here. If we have a plus b to the power of n, we're basically going to have an expansion of a chosen n times, right? Or we could choose a n minus 1 times and b 1 time. And then we could do a chosen n minus 2 times, b twice. And we could keep on doing that until we get a chosen once, b chosen n minus 1 times, and finally b chosen n times. Right? So expanding a binomial term, it involves having the n power, right? So we have like n brackets here, and we're choosing one of two options for each and every expansion. Now there are basically n choose 1 or n choose n minus ways to find this term, right? Because in this case here, right, if we have a plus b 3 times, or let's just say we have 4 of these. So we need to choose a, let's say r times. That means we need to choose b n minus r times. Right? So we use n choose r, right? Either notation works, to show that out of n of these, right? So out of 4 of these, we're going to choose a twice, right? So if you do that, that's going to be, there's either these 2 a's or the other 2 a's, right? So there's a lot of these possibilities. But this shows that we're choosing a twice, right? So you could not just do like 2, but you could do this for any value of r, right? So that's the reasoning why we're going to multiply like n choose n choose n minus 1, n choose n minus 2, and so forth, right? So this is the formula that we see as our binomial expansion formula. So long story short, if we have a binomial term expanded 4 times, right, we're going to get 5 terms, each which will have a different number of a multiplied and b multiplied. Right? So if you multiply a, say, r times, then b is going to be multiplied n minus r times. But we're going to have many ways to find this multiplied expansion. So we would have to multiply either n choose r or n choose n minus r. So we're either choosing a r times, or we're not choosing a for n minus r times. Okay, so that's the idea behind this entire formula. And let's see how this is applied in practice. Okay, so if you already know your binomial expansions, you kind of didn't need to hear the last few minutes, but this is how we solve this problem right here. So first, 448x6 is definitely a term found in this expansion. So every one of these terms will be ax cubed and b, right? So how do you get x6? Well, we got to multiply ax cubed 2 times. And that means b has to be multiplied 6 times. In front of that, we want to do 8 choose 2. Right? So that's how we set up a equation for a and b. 8 choose 2, you could put that in your calculator as 8 choose 2. Or we could set up a equation like 8 factorial over 6 factorial, 2 factorial. This is all in your formula booklet. Then we do a squared, b6, x to the power of 6. That's going to be 448, x to the power of 6. Okay. Similarly, we would have 2880. That's going to be 10 choose 2. Because you want to multiply ax cubed twice and then b 6 times, or 8 times actually. So we're going to get a squared, b to the power of 8, x to the power of 6, then 10 factorial over 8 factorial times 2 factorial. That's going to equal 2880. Okay, so I'm slightly going to erase the right part of this. This part was pretty simple. It was just a demo to get you an idea of what was going on. So let's continue our working here. So based on these 2 equations right here, right, we're going to have 448x6 equals, right, so we have 8 times 7 times 6 times 5, 4, 3, 2, 1. If you expand 6 factorial, it's 6, 5, 4, 3, 2, 1. And then we have 2 times 1. Right? So you can cancel out all of these terms. And we're left with 8 times 7 divided by 2. Right? Then we get a6, or a squared, b to the power of 6, then x to the power of 6. Okay? So basically we have 28 a squared b6 equals 448. Meaning a squared b to the power of 6 is going to be somewhere around 16. Right? So that's 16. That's our first equation. Second part, if we do 2880 is 10, 9, 8, 7 all the way to 1. That's 10 factorial. Divided by 8, 7, 6, 5 all the way to 1. That's 8 factorial. So that's going to keep only the 10 times 9 at the top. Then we divide by 2 factorial. Okay. Then we get a squared, b8, right? X to the power of 6. Right? So x to the power of 6 is also going to cancel that. So this sets up an equation that looks like 2880 equals 45 a squared b to the power of 8. Or that's going to be a squared b to the power of 8 is going to be 64. Right? So that's our equation 2. So we have 2 equations right here. We're going to solve for this. Right? So how do we solve for that? If a squared b6 is 16 and a squared b8 is 64, we could opt to divide both sides, right? So we could divide equation 2 by 1. So left side divides by the left side, the right-hand side of the equation divides by the right-hand side, right? So we have a squared b8 over a squared b6, that's 64 over 16. B squared is 4, right? So some of you might question, wait, is this legal? Sure, we could divide like 64 by 16, but how do we know that a squared b6 is not a 0, right? Because that's the case, right? That's like the most problematic case. We don't want to consider any possibility of dividing by a 0, right? Thankfully, the question says a and b must be greater than 0, so it's perfectly fine to divide both sides by a squared times b to the power of 6, right? We have the knowledge and the guarantee that this is definitely a non-zero term. So we get b squared is 4. B is going to be plus minus 4, right? What a headache. There's 2 plus minus 2, right? So it's a headache. There's too many things to consider. But again, b and a are both positive, right? They're greater than 0. So b is going to be a 2, right? So if b is a 2, what does that make a, right? A squared b8 is 64. 2 to the power of 8 times a squared is 64. So since 2 to the power of 8 is 256, right? So a squared times 256, that's 64. A squared is 1 over 4, so a has to be 1/2, right? So a is 1/2, b is 2. That's what we get. Okay, so setting up this equation is pretty simple. Like the main solution you're going to write in your paper is going to be this part right here. You're just going to do 448 x to the power of 6 is this thing. 2880, 10 choose 2, right? Like 2880 is going to be 10 choose 2, a x to the power of 6, b 8, right? So we solve for that. That's like the main part of the equation. Then you just gotta make those calculations on your calculator and find that a is 1/2, b is 2 using system of equations. But you have to understand the whole theory of binomial expansion. Okay, so that's why I took some time earlier to give you a brief recap, but you don't have to watch the whole thing if you're familiar with it, right? And before we move on, I'm just gonna show you on the calculator like how you can do these permutation and combination calculations, right? So if you're asked like how many ways are there to choose n, choose r, right? So how can we choose r out of n possibilities, right? So there are like n different times you have to make a choice. We need to do some action for r of them, right? So NCR. You can conveniently find this calculator value on your calculator. We can do probability, right? So we have permutations, combinations. So combinations is where order doesn't matter. So I want to do 8, choose 2, right? So calculator, tell me how many ways are there to choose 2 things out of 8? Right? So 8, choose 2, that's going to be 28, as you saw earlier. And if we do 10, choose 2, right? So combinations, 10, 2, That's going to be 45, right? And there's symmetry here, right? To say that we're choosing 2 out of 10 is like saying we're not choosing 8 out of 2, right? To choose 2 out of 8 is saying we're not choosing 6 out of 8. So you'll see that 8 choose 2 is going to be the same as 8 choose 6, right? So that's also 28. And 10 choose 2 is going to be the same as 10 choose 8. So 10 choose 8. And we can also do permutations. So permutations is when the order of choice matters, right? So how can you choose 2 out of 8 people? But if you choose A and B, that's counted separately as B and A because the order of selection matters. So these you can also do on your calculator. Okay, now let's move on to section B. So the last 3 or 4 questions in section B tend to be a bit harder. They're extended, right? So it's not just like a short one-off problem. It's like there's a series of subset of questions, so you gotta know where this story is taking you, right? So let's go through this one by one. Right? The first one, it's a equation that involves exponents, right? So e to the power of negative 0.08t. This is going to give us the temperature as a function of time, right? So with or without using your calculator, you might want to see what this is going to look like, right? So we have a exponential decay function that goes like that, because we know as t goes to infinity, e to the power of minus t, that's like 1 over et, that's like 1 over infinitely large number, so it's going to go to like 0. So normally, this is a exponential decay function. But we have a plus 21 here, so I'm guessing this term goes to 0, and we have our temperature reaching 21 degrees Celsius, right? So this is the kind of graph we might have, so let's keep that in mind as we go through these problems, right? So this is actually Newton's law of cooling, which says that if you have this body of high temperature, right? So T hot, and then we have our surroundings, which is temperature cold, like colder than is. Then we know heat is the non-mechanical transfer of energy from high to low temperatures. So heat is going to flow from hot to cold until both bodies reach thermal equilibrium. So this hot temperature is going to keep going down, right, until it reaches Tc. So we know that if this is our surroundings, then our body is going to kind of reach this over time, right? So this is Newton's law of cooling, but let's focus on what the question is asking, right? So that was just like a brief overview of what's going to happen. First things first, find the initial temperature of the T. Okay, so since this is our function, right, so we put in time and we get our temperature H. So the initial temperature is when T is 0. So we do H0, which is 21 plus 75 e to the power of negative 0.08 times 0, which is 21 plus this thing, right, e to the power of 0. Anything to the power of 0 is 1. So 21 plus 75, that's 96 degrees. Right? So we start off with 96 degrees. The T is obviously hotter than the surroundings. It's going to cool down all the way until it goes to 21 degrees. Right? So the next part, let's do part 2. Right? So find the temperature of the T 3 minutes after it is poured. So 3 minutes, that's T equals 3. So we just need to check the units, right? Because sometimes the units might be in seconds, not minutes, but let's just look at what HT means, right? So if you have T minutes after the T is poured, the temperature is going to be H. So we just need to find H3. If this was in seconds, then 3 minutes would be 180 seconds, so we might have had to do like H180, right? But that's not the case here, right? So I just want to emphasize 2 points. Read the question carefully, RTQC, and check your units, CYU, right? Because we know that our units are in degrees Celsius for H and minutes for time. So we can just plug in 3 for T. So we have 21 plus 75 times e to the power of minus 0.08 times 3. Right? That should give you somewhere around 79.9970, which is roughly 80. Right? So our temperature after 3 minutes is 80 degrees Celsius. So whenever you're putting this in your calculator, make sure you write the 3 as part of the powers here. We don't want to write that in here or anything, right? So let's quickly go to the calculator, see what you have to put in. So you have to write your expression like this: 25 plus 75 times e to the power of minus 0.08 times 3. What often students might do is they might do something silly where they have like negative 0.08, all the right places, but then later on they might do times 3 here, right? These two are clearly different. So make sure whether the 3 has to go at the top as part of the exponents or as part of, somewhere outside. Right? So make sure you keep all the brackets in place. Make sure all the numbers are properly integrated into either the exponents or the base here, because that makes all the difference, right? Whether it's order of operations or whether it's having a complete different set of calculations to make, you got to be careful with how you use your calculator. Since we had 3 minutes and we had the function to calculate the temperature at 3 minutes, that gave us 80 degrees Celsius here. Right, so we had 96 degrees Celsius at the beginning. Later on, it becomes 80 degrees Celsius. Now, we do h prime 3. So we find the expression for h prime t. 21 is a constant that goes away if you differentiate it. E to the power of negative 0.08 t stays as is, but we got to use the chain rule. Right? So we have 75 times, we want to multiply the negative 0.08. Right? So that should give us somewhere around negative 0.6. Right? So that should give us somewhere around 6 actually. So that's negative 6 e to the power of negative 0.08 t. And h prime 3 is just substituting in t equals 3. So negative 6 e to the power of negative 0.08 times 3. That's going to be somewhere around negative 4.72 degrees Celsius per minute. Right, so since h prime is like the rate of change of temperature over time, we know that our unit should be degrees Celsius per minute, right? And I know it's tempting to write like per second or per hour because it's per unit time, but in this case, the default units are minutes and degrees Celsius, so you got to stay faithful to our units. Okay, so interpret the meaning of your answer, right? So it's basically, if we have our h that's decaying over time, h prime is giving us a gradient. So if you were to draw a tangent line at any point along this graph, the slope or the gradient of the tangent line, in this case, would measure the instantaneous rate of change, right? Rate of temperature change. Right? So we want to be more specific in the context of this problem. It would be how much the temperature is cooling, right? So negative 4.72 means that the temperature is cooling by 4.72 degrees Celsius per minute at time is 3 minutes, right? So 3 minutes after it started cooling, we are losing 4.72 degrees Celsius per minute. So we're losing 4.72 degrees like per every minute, right? So will this rate continue on? No. We know that this is a continuously changing rate. If anything, we know that the rate of cooling kind of slows down as time goes on. So we need to substitute in our right value of t each time. But in this case, we just find the general expression for rate of cooling of temperature, h prime t. We put in t equals 3, so 3 elements, right? One is that at 3 minutes, the temperature is cooling at 4.72 degrees Celsius per minute, right? So those 3 points are what we need for the full points here, right? So that will give you 2 marks. Mention that its time is 3. The negative sign indicates that temperature is dropping, and the exact quantity with units is 4.72 degrees Celsius per minute. Okay, next. After k minutes, so when t equals k, the t will be below 67 and cool enough to drink. So we want to look for hk is going to be less than or equal to 67, right? But since it's k minutes, I guess we got to round, right? Because it says k belongs to a set of z plus. Z is integer, so k must be a positive integer. So we get 21 plus 75 e to the power of negative 0.08 k. We want that to be equal to 67, right? So I'm just going to use the equal sign here. Then before we put this in your calculator, I would want to simplify this. So I would do 46 equals 75 times e to the power of negative 0.08 k. Then e to the power of negative 0.08 k would be 46 over 75. Then I can rearrange this using my knowledge of logs and bases. So if you have ln a equals b, that's like saying e to the power of b equals a, right? So this thing would go to the bottom here. So I would say negative 0.08 k is like ln 46 over 75. So meaning k is going to be 1 over negative 0.08 ln 46 over 75. So this is one way to go about it. I prefer this method because you can just write this full expression into your calculator. But you don't have to do it this way. You could opt to maybe graph, right? So you could graph the original ht value here. So you would input, say, y1 is 75 e to the power of negative 0.08x plus 21. Then you could graph y2 equals 67. Then you're going to get a crossover point at k, right? So you can use the graphing method, or you can use this algebraic manipulation, then calculate method, right? So let's move on to the calculator to see both solutions. So what I want to do is I first want to do ln of 46 over 75, right? So that was what I was going for, right? So ln 46 over 75 divided by negative 0.08. So I would divide this by negative 0.08. That gives me 6.11. Okay, so at 6.11 minutes, our tea is going to cool down to 67 degrees Celsius, right? So I might want to wait until the 7-minute mark so that it's cool enough to drink. Okay, next let's check the graph here as well. So if you were to plot the original graph of 21 plus 75 times e to the power of negative 0.08x, right? So instead of t, we would write x here. I would want to go into my settings. So I know that I might want to go from t is maybe -1 to, say, 10. Right? Since we know that k is going to be the 6-minute mark. But let's just actually graph it until the 30-minute mark. Okay? And then we know that our temperature starts from like 90-something degrees. So let's set our temperature range from 0 to 100. So we know that our temperature is not going to fall below 21. So this is what we get. Let's add another graph. So actions. Right. So another function we might want to add may be so graph entry function. If you have this equals 67, right? We might want to find the intersect. So analyze graph, find the intersect between these 2 points, right? So we know when time is 6.11, the temperature falls down to 67, right? So by the 7-minute mark, that's the first integer value for which the temperature is less than 67, right? So we just looked at 2 ways to use our calculator to find our solution here. So we figured that from this, k is going to be 6.11, or that the 2 graphs intersect at 6.11. So the least possible value of k is going to be k being 7 minutes. Right, so 7 minutes after the tea starts cooling, we're going to go all the way down from 96 degrees Celsius to 67 degrees Celsius. Right? So for part D, k is going to be 7 minutes. Next, find the temperature of the room as ht approaches the temperature of the room, which is constant. Okay. So basically what we said was, we know that this graph is going to have an asymptote at h is 21 degrees Celsius, right? The reason being, 21 plus 75 e to the power of minus 0.08 t. So what happens to this whole expression as t is taken to a infinitely large value? Well, we know that this thing becomes a 0, right? So we're going to approach 21 and no less than that, right? Because this expression cannot be negative. The closest it gets is 0, right? So we can assume that the temperature of the room is then 21 degrees Celsius because we see our temperature of the T reaching 21 degrees Celsius. Okay? And what's H prime T as T approaches infinity? So as T goes to infinity, we know that it's no longer changing. It's stabilizing. It's flatlining. So H prime T would just have to be 0 because over time it's going to stabilize and basically just equal, and it's happy to stay at the room temperature. So the limit of H prime T as T approaches infinity, right? So we'll just write this as T going to infinity, H prime T is 0, right? So that was a problem using calculus and modeling, right? And we're done. So the key things to look out for in this problem was the units, right? Make sure you're keeping the minutes and degrees Celsius, and you gotta kind of understand the physical context of where this problem is taking you, right? So Newton's law of cooling, that's something to read about. You don't need to know that to solve this, but it might help you kind of understand the problem, right? So in this case, we know that it's asymptotic in nature, right? Temperature's dropping to the surrounding temperature, right? So that's just about it. I think that was pretty straightforward because it just asks you to find HT, H prime T, and it constantly just questions you, like, what do you think this means, right? So that was number 7. Let's move on to number 8. Okay, so we have a two-way table here, right? We have our population. They're either milk chocolate lovers, dark chocolate lovers, they're children, they're adults. So there's 4 different possibilities that everyone fits into. Okay, so we know that there's a total of 160 people, and I guess everyone falls into one of 4 categories, and then we have some conditional probabilities going on. So let's dive in. So first of all, what's the value for P and Q? Well, we know that there's 160 people total. Q should be 100, right? And then P should be 48 plus 12, that's 60. So that's 12P and 100Q. Right? And we would want to know what X and Y is, but I guess we can't do that just yet. So we'll have to move on to the next problem. So if we choose 3 people, what's the probability that they're all adults? Okay, so could we just do like, okay, there's 100 adults out of 160. We're not doing this once, so we're going to do this 3 times, right? So would you take this approach? No, right? Because that means the probability of selecting an adult is like same throughout. That would imply like independent events, but we're not independent here. These are clearly dependent because who you get on your first draw, right? Whether you're a child or you're adult, right? That's going to influence the remaining probability, right? Because if you take the first adult, right, that's a 100 out of 160 chance, but then you have 159 people remaining with 99 adults. Then if you choose an adult again there, we're going to have 158 people and 98 of them are going to be adults, right? So we have to use this expression to find the probability of choosing 3 adults, right? So using your calculator, that should give you somewhere around 0.241372, or rounding to 3 thick figs, 0.241. So just in case you might have to use this value again, I would just store it, right? Because we want to round at the very end. We don't want to use rounded values midway. Okay. Now, C says P A given M, right? A bar M is 1/3. Find the value of X. Okay, so what does this mean? This is conditional probability. So P A given M is that the probability of being an adult or choosing an adult given that he or she already likes milk chocolate. Right, so instead of the full 160 of our sample, we're limiting our search to 48 plus X. Right? So out of the possible 48 plus X people who already like milk chocolate, So we don't need to look at the full 160. We only look at the 48 plus X people who like milk chocolate. What's the probability that we choose an adult, right? Because there's children who like milk chocolate, there's adults who like milk chocolate, but we want to look at the probability of being an adult here. So that is going to be 1 over 3, right? So that's basically solving for X here. So 48 plus X is going to be 3X. So 2X is 48. So X is going to be 24, right? So it says find the value of X. X is going to be 24. Okay. So technically speaking, the formula for conditional probabilities looks something like this. If you have probability of A given M, this is simply a probability of A and M over probability of M, right? Which is basically what we did here, right? What's the probability of having a milk chocolate lover? Well, that's 48 plus X over 160. What's the probability of them being an adult who likes milk chocolate? Well, that's just X, right? So the probability of choosing that is X over 160, right? So what we did was more of like a colloquial, like informal way of doing it, but it gets a job done, right? So we just set up X over 48 plus X, that's 1 over 3. That means X is 24. Okay. Next, let's do part 2. If a person chosen at random, right? Okay, so if a person is chosen at random, so we're choosing from all 160 of these people, what's the probability that it's an adult who prefers milk chocolate? Okay, so the adult who prefers milk chocolate, that's basically X here. So this is a no-brainer, right? So we're choosing 48 possible people out of 160. That simplifies to adult who, oh wait, so it's 24, my bad. So X was 24. So what's the probability of choosing 1 of 24 adults who like milk chocolate out of 160 total? That simplifies to maybe 12 over 80 or 6 over 40, 3 over 20. So that's going to be around 0.15. Okay, then are events A and M independent? Justify your answer. So when it comes to these problems, determining independence or dependence might have some like contextual judgment. Like we know that rolling a die is independent because whatever we get on the first roll, that's not going to influence what we get on the second roll, right? If you're drawing marbles out of a bag without replacement, that's dependent, right? So there's a lot going on with this situation here. But instead of going through that contextual like argument of are these events independent, I would just go with the formula right away, right? So if these events are independent, then probability of A times probability of M, that should equal probability of A and M. Right? So we know that probability of being an adult, that's 100 out of 160. Times probability of someone liking milk chocolate, well, since X is 24, Y is 76. We know that there's 72 milk chocolate lovers. So 72 over 160. That should give us 7,200 over 160 squared. That would be somewhere around, if we simplify this, it's like 5 over 8 times, I guess 36 over 80, 18 over 40, 9 over 20. So that gives you somewhere around 45 over 160, or actually that should be 9 over 32. Right? So probability of A times probability of M, that's 9 over 32. Let's look at probability of being an adult that likes milk chocolate. Well, we found that to be 0.15 from earlier. So clearly, these two are not different, right? So don't just leave it at that. You need to write the full statement. They are not independent because probability of A times probability of M is 9 over 32, which is not equal to the probability of A intersect M, which is somewhere around 3 over 20. Right? So that's the full statement you need to get all the marks. Okay? So we need to state that they're not independent. We need to show evidence that we know the formula, right, which is a condition for verifying independence. And we got to put in some hard numbers there to see or to show that they clearly don't work. Okay, last part, it's a bit tricky. You got to know what the question is talking about, because it says the survey is representative of the entire population. So basically, if there's 100 out of 160 adults, we can scale that out to the entire city, right? So out of every 16 people, 10 of them are adults. Same for the, like ratio of chocolate preference. So it says 10 people are chosen at random. What's the probability that at least 5 of them prefer dark chocolate, right? So this is saying we're going to conduct 10 experiments, right? We're going to flip a coin 10 times, right? So we have n trials. So the word I'm using here is in line with binomial distribution, right? So let's say there are 10 trials. The outcome of these trials, right? So there's a probability of P where the outcome is that the person prefers dark chocolate. Then there's going to be a 1 minus P probability where this person does not prefer dark chocolate. So it's like flipping a coin 10 times, right? We're choosing 10 individuals, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Out of those, some will prefer dark chocolate. So let's write that as maybe D. Some will not prefer dark chocolate, maybe like D prime. So we're going to get a bunch of these different possibilities where there's like a mix of dark chocolate lovers and non-dark chocolate lovers. But we want to look for cases where 5 out of 10 like dark chocolate, or 6 out of 10, 7 out of 10, 8 out of 10, right? 9 and 10 out of 10 like dark chocolate. So in order to do this manually, what you would do is something like this. We know that the probability of preferring dark chocolate, right? So let me just take out the earlier steps from here. So the probability of someone liking dark chocolate from this situation is 88, right? So 88 out of 160, which is roughly 0.55. That's a probability that one person is going to like dark chocolate. So if you have 10 adults, we might want to look for the probability of XD. So let's say D is going to be the number of people liking dark chocolate. Right? So D can be anywhere between 0, 1, 2, all the way to 10. Right? So number of people out of 10. So if you choose 10 people, D is going to be anywhere from 0 to 1. I mean 0 to 10, right? So probability that D becomes like D, small d, where D is 0, 1, all the way to 10, can be found as 0.55 to the power of D, and then 0.45 to the power of 10 minus D. Right? Now, out of the 10 people, like which D of them, right, will like chocolate? So we would have to do 10 choose D. So for instance, if you have D equals 3, we would do 0.55 to the power of 3, 0.45 to the power of 7, then we do 10 choose 3, because 3 out of 10 of those will like dark chocolate, or 7 out of 10 of those will not like dark chocolate. Okay, so we would have to do this, but we have to cycle through D equals 5, 6, 7, 8, 9, 10, and we have to add all of those probabilities. Okay? But we can achieve this calculation using binomial CDF on our calculators. So binomial CDF basically does, we have 10 trials, we tell the calculator the probability of a successful event is 0.55. Then we basically say, okay, I want to look for the lower bound 5, upper bound 10. Basically, I want to look for cases where 5, 6, 7, 8, 9, 10 people like dark chocolate with a probability of 0.55, right, for each case, for each person, out of 10. right? So we're going to go over to our calculators. We're going to use binomial CDF with n equals 10, p equals 0.55, L is 5, U equals 10. Right, so as I said earlier, we're going to use binomial CDF. So you go to Stats, Distributions, binomial CDF. So we have 10 trials. The success probability is 0.55. The lower bound is 5. Upper bound is 10. So the calculator automatically finds, right, out of 10 people, 5 or more will like dark chocolate. So that's 0.738437. We can just write that as 0.738. Okay, so the last 4 marks, this is a bit tricky because unlike earlier on where we're just like talking about probabilities and finding like conditional probabilities, we now are hit with binomial cumulative distribution. So if you recognize that, it should be an easy 4-pointer. If not, you would have wasted a lot of time trying to figure out what this means. But always think, does this apply? So think of this as like a coin flip test. Can I think of this as a coin flip, right? Are there 2 outcomes and are there independent trials, right? So picking people, that's like the independent trial. The coin flip would involve dark chocolate, like or not, right? So that's binomial CDF for you. Let's move on to the next. Okay, lastly, we have a gutter that's shaped by, I guess, folding this sheet metal. So I guess we're folding this sheet metal to have some straight regions and a arc here, a circular arc. And this is a cross-sectional area of the gutter. Okay, so the height we want to keep at 10. So out of the 45 available length, like 10 are going to the sides, and I guess AB, this is the arc length with 25 length. Okay, so arc AB is a circumference of a partial circle, right? So you could imagine there being some type of circle here. And I'm guessing we're going to find out the different dimension lengths, angles, and areas here. Okay, so let's begin. If AOB is theta radians, let's show that theta is 2.08. So since it's a show that, we never want to touch this value. Like it's like tempting to use, but know that this is the end goal. So we have to pretend that we're blind and we don't know what theta is going to be. Okay, so we know that arc length AB is 25 centimeters. But we also know the formula for arc length, r times theta, where theta is in radians. So we would do, since the radius is said to be 12, we would do 12 times theta is going to be 25. Theta is 25 over 12, which is roughly 2.08 to 3 sig figs. Right? But in our case, yeah, so if you do 25 over 12, it is indeed 2.08, but we want to show maybe a bit more, right? So we don't want to just end it as 2.08. We might want to just go to the calculator to do 25 divided by 12. It's convert to decimals. Right, so 2.08333. So you might want to write this is 2.08333, which is roughly 2.08. Hence, we show that theta is 2.08. Okay, next, let's find the cross-sectional area of the gutter. Okay, so we want to find this shaded area. Now, how do we do that? Okay, one approach might be okay, so we could try adding the sector AOB, right? So we have this entire sector here. And then we could just add this funky shape right here. Easy peasy, right? But the thing is, this is not too straightforward to get, right? So what we could do is we could do 1/2 r squared theta, since that's the formula for sector area. Then to find this one, we would do 10 times W, right? But then we have to count out this triangular area. So area of a triangle, we can use 1/2 AB sine C, right? So 2 side lengths multiplied, 1/2. Then we do sine C here. So we could do like minus 1/2 12 squared sine theta. That's one way to do it. Or we could do the rectangular area plus this area right here. So this would be 10 times W, length times width of a rectangle. How do you find this chord slash, so this like section here? Well, this part is just the arc minus the triangle. So again, we would just have 1/2 r squared theta, where it's just 12 squared times theta, minus 1/2 12 squared sine theta. So either way, we're looking for the same expression. Right? So however you approach it, we're going to find the area using 10 times W plus area of the sector, which is 12 squared times theta. Now we found theta to be 2.08, minus we subtract the area of the triangle. Right? That's what we do. So we're basically double counting the area of the triangle, so we subtract that. Now, we want to find what W is going to be. Right? So we know that theta is 2.08 minus 444 over 2 times sine 2.08. Now, let's go on a tangent here to find what W is going to be. Right? So W is the longest side length. Right? So if you kind of move this down here, it's the longest side length of triangle AOB. Right? So if you imagine ourselves to have 2.08 radians, the two lengths here are 12, we have W. So what is our W going to be? This is a typical SAS situation. We're given info about a triangle, particularly the two sides and the angle between, and we want to know other angles or sides, right? So if you have a SAS situation, we always do the cosine rule. If we have the SSS situation, if you know 3 side lengths and we want to know any of the angles, we again use the cosine rule, right? In all other cases, I would prefer the sine rule because, you know, sine rule calculations are easier. But SAS and SSS, these are the two cases where we can't use the sine rule, right? So I know it's a bit dreadful having to set up this formula, but we got to solve for what W is. So we have 12 squared minus 2 times 12 times 12, then cosine of 2.08. And I think I said very earlier on that we have to use radians for all cases unless it's specified as degrees, right? And since we're dealing with radians, this is exactly what you put. So W squared is 144 plus 144 minus, so 144 times 2, so that's 288, cosine of 2.08. So W would be square root of 288 minus 288 cosine 2.08. So we've got to hop over to our calculator to see what that means. Okay. So a lot of students tend to mess up this calculator part, but if you don't make any mistakes, you should be fine. So square root 288 minus 288 cosine 2.08. And to be exact, it wasn't 2.08, it was 2.08333, right? We have our value saved from earlier. And I'm going to hit enter, but I'm probably going to have to check if the settings were in radians. Okay, so it is in radians, so I know that W is going to be around 20.7. Okay, so W is 20.7, so I'm going to write this as 10 times 20.7. So that's going to be 207 plus 72 times 2.08 minus 72 times sine of 2.08 radians. Right? So just to get in the habit of using like these stored values, I'll just go over the calculator again. So what we do is, just to make sure that we're using the right values, I'm just going to do 20.7179 times 10 plus 72 times 2.08333 minus 72 times sine of 2.08333. That should give you 294.43. Or roughly 294, right? So it's enough that we remain in 3 sig figs. And since it's a cross section with all quantities given in centimeters, it's 294 centimeters squared. So that's how you do part B. Yep, so W, all of these were in centimeters, so we get our final answer in centimeters. Next, the rate at which rainwater enters the gutter is modeled by this. So R prime T is that. So if you were to say integrate R prime T with respect to time, and if you put in like the starting time and finishing time, that would give the total amount of water that came in. Right? So that would be like the total amount of water that came in, and we have a 60-second period, okay? And if the volume of rainwater entering the gutter is greater than that, it will overflow. Okay, so we're gonna basically test if the water that came in is greater, right? So volume of incoming water, right? So the volume of rainwater that entered, that's going to be integrating from 0 to 60, this full expression, 50 cosine 2 pi t over 5 plus 3,000, right? And then we do dt, right? So let's try to find out what that's going to give us. Okay. So if we do that on our calculators, that's going to be, so we can use our integrate from 0 to 60, and our expression is (50) times cosine of 2 pi times, instead of t, I'm going to go with x, right, divided by 5, close brackets, to avoid any confusion, and then I have x. So that should give me the total volume here. Oh, and I also have to add plus 3,000, because that's the expression. That is 180,000, right? So that much has just come in from the rainflow. Right? So that turns out to be 180,000. So what do we compare this against? Well, we said the cross-sectional area was 294, but that's not what we're comparing, right? We have to compare apples to apples, not apples to oranges, right? So we know that this cross-sectional area was 294, right? But the volume coming in was 18,000, so 180,000. So we got to compare this to the entire volume here, which is this sectional area times 600, right? So we got to make sure we're comparing volumes. Otherwise, you would be comparing cross-sectional area to volume, which wouldn't make sense. So back to our point here on C, right? So the incoming rainwater is 180,000, 180K cubic centimeters. The volume of the gutter was 294 centimeters squared times 600 centimeters. That's roughly less than 180,000. So that should be somewhere around 177. So we know that the gutter will overflow. Right? So you can say that the gutter overflows. Because from the earlier cross-sectional area that we found that the total volume of the gutter is less than 180,000, which is what the incoming rainwater volume was. Okay. And that just about concludes paper 2 for 2022, May paper 2 Timezone 1. And so hopefully you were able to follow along. If there are any parts that you're unsure of, you can rewatch those again and we'll discuss it next time.